All right, let's talk about secure cloud connectivity with Nerves. I'm Alex, founder of Redwire Labs, product development agency. We specialize in building connected products and work across the stack from front end to firmware. One of the tools we use to build those products with is Nerves. We've got a handful of people that work here. A couple that I was able to bring out are Abelino Romo, principal engineer. We've got Chris Clark, who specializes in product management. He helps our clients with product coaching. One of the big reasons why I care about security is because I worked for a company that went through 2 major security incidents. It was not a great experience to see, but it did teach me some things. One of the things that I learned is I never want to put our clients at risk. Since we do consulting, I don't want to put their customers at risk. It's not great for people to have to go through things like identity theft or a ransomware attack or a cryptocurrency mining scheme. Those things are tough. I don't want to have to deal with the fines and lawsuits that come out of that, and I don't want to lose trust with our clients. So what are some of the common vulnerabilities that are out there to start with? And this is really one of those things that all starts with mindset. So how are you thinking about security? Are you thinking about security? So on one side of this, maybe security isn't even going through your team's minds. Maybe it's not part of a company culture. Maybe there's that rush to be able to ship the product yesterday. And maybe if you're in that case and there is a little bit of talk about security, maybe it's, well, we'll deal with security after we've launched. The problem with that is there's only so much you can change at that point, especially when you're dealing with hardware. Once you've got hardware in the field, how do you add to it? And if you do, there's cost associated with that. The other side of mindset is overconfidence. So some of those things like, oh, well, I work on a Mac. Macs don't get viruses. Macs don't get malware. I don't have to worry about that. We work in the best tech stack. We use Elixir and Phoenix, and Ecto helps prevent SQL injection and things like that. My tech stack will take care of security for me. Or we have a world-class team. I see the smiles. Yes, some of you have been there. So, how often is your team talking about security? How much is security part of your culture? So there is a healthy middle ground here. And it doesn't mean necessarily go out and be a security expert. There is a whole nother field for that. But it's some of the things like just how curious are you and the people on your team? How much do you put into continuing education around, are you brushing up on some of the common attacks that are out there, being able to see a little bit through the eyes of an attacker? And that culture aspect too, is it something that your team has conversations about? Are you comfortable and used to having conversations about this kind of stuff? And this can look like things when you're developing your project, when you're going through your roadmap. Is there a spot on there where you actually said, at this point, we're going to go engage with a pen testing firm. They're going to come in, they're going to go through our product. They're going to make sure nothing's, out of the ordinary in there. People can't get into it. When you're doing software architecture design and review, when you're doing code review, are those the places where people on your team are looking out for spots? And if you see those vulnerabilities, you've got people that'll speak up and say, hey, wait a second. Can somebody get into this piece of code? Should we write this bit differently? Should we design this piece differently? So that's the start. Going into a little more of the technical side here. It's the connection itself. So are you dealing with an encrypted connection? Are you still running off an unencrypted connection? This is something that was really prevalent in the 90s. Luckily, it's getting a lot better today, but this is still a thing today. Some of those common cases that we deal with, if you're dealing with like embedded technology, your device connecting up to the cloud, since you're pushing that out into other people's hands, are they putting that on an open Wi-Fi network? Open Wi-Fi network isn't going to have AES encryption on it that's encrypting that data over the airwaves. Somebody can sniff that data. And that's not necessarily something that takes sophisticated equipment to do. You can do that with a modified Wi-Fi dongle. once you're getting that traffic up to the cloud, are you using an unencrypted protocol? Did you bother to encrypt the protocol? Something like UDP, although not impossible to encrypt, it's typically not encrypted as much as TCP is, for example. UDP is a lot more set up to send smaller messages, datagrams, streaming data, telemetry, things like that. So it can be really tempting not to encrypt that. You might also be on a platform that makes that hard to do too. So if you're working with microcontrollers, for example, it might not have enough horsepower to actually do the encryption. Luckily, that's getting a lot better on microcontrollers these days because they're getting more powerful. The other side of that is, did the vendor provide it in their tooling? So it could be the cost associated with it that adds that friction. So instead of it coming from, I won't call out any vendors, but instead of it coming along with the vendor's tooling, do you have to go to like Wolf SSL and pay them for a license for your SKU to be able to get the encryption? Maybe you've got some pushback from management that they don't necessarily want to pay for that. So those are some things to be thinking about there. Unencrypted secrets are another one that's still pretty prevalent, I hate to admit. But these days, so are you putting your secrets in a password manager? If your secrets are in the cloud, are you making sure to store those in AWS Secrets Manager, places like that? If you're storing them on disk in a database, are you doing things like there's a way where you can use a seed and a initialization vector and an encrypted data value, and you can use that to encrypt certain fields in your database without having to encrypt the entire database itself. So are you using these type of methods to keep the stuff private that's supposed to stay private? Kind of going along with this then is reusing or sharing those secrets. So password reuse is one of the huge things. It's obviously not great to do it between users. You really shouldn't be doing it between devices either. And the other side of this that gets used a lot between devices is if you're using private keys on a device, are you using the same private key across your fleet? So now all somebody has to do is compromise that private key of one device in the fleet, and now they can impersonate anything they want to in your fleet. They can get to anything on your server that a device could get to. And this is going to make it a whole lot more of a pain for you to have to re-roll that key. Because when you push the new key out to the rest of your fleet, are you still sharing it? Did you actually update your strategy in deploying that key at that point? Does the attacker still have access to your system? Are you deploying your new key right back to the same attacker? So there's those types of issues to think about. And kind of along with this of how somebody can get stuff off your device is, are you using removable media? So do you have a Raspberry Pi or something with an SD card on the front or the back of it that somebody can just walk up, take the SD card out of it, and plug it right into their computer, and now they've got access to all the data on your device? So this is especially one of the things to be thinking about with hardware, because you're shipping hardware to somebody you don't trust. It's going to an untrusted party. Versus when you're shipping stuff, there's still some issues here, but I'll say it's a whole lot easier when you're shipping to your own on-prem data center or you're shipping to your own cloud infrastructure, because you control that hardware. Your device is going out to a stranger, and they can do whatever they want with it once you put it in their hands. You can't stop them from getting into it. So the other type of thing here is a SIM card. Are you using a removable SIM card that they can pull out? Number one, can they get to your cellular data plan with this if they pull it out? Number two is SIM cards actually come with a device identity as well. So if you're using that identity as part of the device or as part of your network or as part of your fleet, are they able to spoof the identity of one of your devices by removing that SIM card from it? So if you know a little bit about storage, you might be thinking here, well, can I move this to like eMMC flash? Because then I'm at least on a chip that somebody's not going to be able to pull off the board unless they have really good skills on removing that type of stuff, which there are. So one of the things to be thinking about here is, what level of attacker are you trying to keep out of your system? There's this balance between how many barriers should you put in place versus when does it just cost too much for some, to keep somebody of a certain skill level out. So going down the eMMC route, it's better than a SD card that they can pull out, but there are still ways that you can get into an eMMC because you can write firmware on there in the first place. Therefore, you can also pull firmware off if you know what you're doing. One of the ways you can do that is through U-boot. So this is a screenshot off of the BeagleBone Black where I'm in U-boot. This is the bootloader. We haven't got into Linux. We haven't got into Nerves, any of that stuff yet. This is just the very first thing that the system starts up. And already at this point, I can see the eMMC device. I can see all of the partitions on that device, and I can see files on that device. So I can now go in here and grab this off through a serial cable, and I've got access to all these files. So U-boot's pretty common to use in production. It is a good tool. If you're using U-boot, make sure to at least lock it down with a password. Better yet, in production, disable the U-boot console in production. That's a good way to keep this secure. The other thing that's an option here is using a bus sniffer. So this is an electrical method. An eMMC chip uses the same electrical interface as an SD card does. It's the SDIO interface. So if you can gain access to that electrical interface, say scraping the solder mask off of pins, or if somebody left you a convenient debug header on there that you can get to, you can wire that into something like a bus sniffer. You can plug this into a flash card reader, and now you have access to that eMMC device. So those are some things to think about there. Let's dive specifically into the embedded connectivity part of this. One of the architectures that we typically use and typically encounter starts with this at its core. Sometimes we can get a little more complicated, but at the gist of it, we have an embedded device on one side. We're talking through the cloud, and we're either talking to a broker, messaging broker like MQTT, or we're talking directly to a backend, so like a WebSocket to a backend web server. The other connection we typically have is to a firmware over the update service. That might also give us remote management as well. So like in the case of Nerves Hub or Nerves Cloud, you get remote management back to the device there too. So what we're specifically talking about in this case are IP-based methods. We're talking about Ethernet, like wired Ethernet. We're talking Wi-Fi. We're talking cellular, LTE, Cat-M1, those types of things. What we're not talking about here are things like LoRa or Thread or Matter or Zigbee or Z-Wave or Digimesh or any of the 802.15.11 stuff that usually has like a gateway that helps interconnect those products. All of these types of things have their own way they do security. All that stuff could be its own talk. So how can you start defending against some of this stuff in terms of connectivity? One way you can do that is with a VPN. This is going to push that encryption down to the network level. So when you're using a VPN, in that like microcontroller UDP example, if you just can't get the encryption on the microcontroller, if you just can't get it in the device, if you're using a legacy application where you don't really have the ability to modify its code, maybe one of the approaches there is create a secured network. So now you're encrypting the data as it goes in and out of the VPN to your device or to your server. And you're creating a secure tunnel across the cloud to be able to get that data back and forth. And now your applications don't have to know anything about that encryption layer. But the flip side here is this kind of like turns it into a DevOps problem. You're now dealing with an infrastructure layer that you have to maintain rather than putting it in your app. So that's kind of the trade-off there. One of the cool things too with VPNs is WireGuard is supported out of the box in the Linux kernel these days. So if it's not enabled for you yet, it's typically just a matter of flipping that on in the kernel and recompiling it. Now you've got access to that. VintageNet WireGuard is also one of the Nerves tools to be able to configure WireGuard from a Nerves application. So there's some native tooling built in there that can help out with this. So the other side of this is using TLS and moving that encryption up into the application layer. So this is where both the device and the server know about the encryption. They have credentials that let each other speak to each other. And that application is the thing that's creating the secure connection through the cloud. This is done with asymmetric keys. This is probably going to be a review for a lot of you, but this is going to get everybody on the same page. I'm going somewhere with this. So done with public and private keys. There's a private key that's a giant magic number. There's a public key, which is a smaller number typically derived from that, and there's magical math that creates these. There's a connection handshake that happens in this process. The first part of this is just a plain old vanilla unencrypted TCP connection, where the client will say, hey, I want to connect. It wants to synchronize. Sends that over to the server. The server says, okay, let's connect. And they've established this unsecure, just vanilla TCP connection at this point. The next layer of that is escalating it to an encrypted TLS connection. And they'll do a certificate exchange and some other stuff in here. And at the end of that, now you have an encrypted connection. So another part of this is, how does the client and server, if they can encrypt their connection with each other, how do they know they can trust each other? And that's where certificates can come into play. So there's a concept of a certificate authority. And long story short, if the server trusts that certificate authority and the client trusts that certificate authority, if the client and server have never met before, never connected before, that's one way that they know they can trust each other, because they trust this shared authority. So there's a certificate bundle that goes along with that. So like when the client is going to connect, it can, before the connection happens, in advance, the client has attained a certificate from that authority, a signed certificate. It passes that to the server during its connection. The server is able to check that and say, oh, hey, okay, I got a certificate from the authority that I know about, that I trust. I'll let you connect. A cool thing that can ride along with this certificate is a device identity. So this is called the common name field, or CN field. We use this a lot for embedded, for being able to embed like a serial number or some other way that we reference that device. And so now the cool part about this is, during that connection process, this layer 4 connection, you can also be establishing that device identity and know who's connecting to you as a server. And you don't have to wait till that connection's complete and do it in the application layer. So it saves you from having to do that in your own custom protocol, your own application layer protocol. You can know this at connection time. So once we've gone through this process, we end up with basically 3 files we care about: a private key, a public key, and a device certificate. And now I said files, and I just talked about the SD cards. So the problem here is, now somebody can get these files. So how do we keep them from getting the files? One thing that might be going through your head is, let's encrypt the disk. And that's one way to do it. Lars talked about this last year, so feel free to review his talk if this is looking interesting. There are trade-offs to disk encryption, though. So on one hand, yes, it can help keep other people out of your system. On the other hand, it can help keep you out of your system. So when you've got a device in the field, depending on what failed, you're inevitably going to have failures and RMAs that you have to work with. When that device comes back to you, if you've encrypted your disk, and depending on what failed, how can you get your diagnostic data off of the disk to know how to diagnose the problem? So I'm not saying disk encryption is good or bad. I'm saying it's something to think about based on your use case. And so is there any other thing to do where, if we care about encrypting the connection, we can deal with just the connection part and not have to tangle that up with the disk part too? So enter the ATECC crypto chip. This is a little chip made by Microchip, and they call it a secure enclave. Basically, it holds secrets. And there's 2 variants of this chip. There's a vanilla version of it that you can program yourself, and it's basically lets you set the layout and things of things you might want where you want them, so you can put the private key, public key, whatever, in different places. They have a pre-provisioned version of this that you can order directly from them called Trust and Go, And when you order these, they come along with a manifest file that you can ingest, and you can use microchip certificate bundle along with this as well. If you're ordering these, they come in 2 different part numbers. There's a single wire interface that has CZ in the part number. Do not order that one. It doesn't work with Nerves. So for Nerves, you want to make sure you have the I2C interface. It has DA in the part number. There's a couple libraries to work with this. So if you're especially flashing the vanilla version, NervesKey is an opinionated library on how to store stuff in the chip and how to work with the chip. So for probably 90+% of the use cases, NervesKey is a great place to start and will probably do everything you need it to do. If you need to dive down and do any lower level stuff, NervesKey is based on the ATECC 508A library. The name is slightly misleading because it also works with the 608A, 608B, those types of chips as well. So don't necessarily think about it as only working with the 508A part number specifically. The other thing here is I've built a live book for this. It's contributed up to the open source official Nerves live book. This can not only be helpful in development for going through and provisioning a chip, but handy in manufacturing too. So when you have to write the instructions for your assembly tech on the factory floor to go through and do the firmware flashing, do the provisioning, if you want to go the live book route, this is something that already has the instructions followed by the source code that's executable directly in the live book for a tech like that to be able to use. The key has a couple different slots in it. Number 0. There's 16 slots, 0 to 15, starting at the private key. The private key here is something that's write once, and you actually can't read it, which is nice. So the private key is stuck in that chip. So anytime you want to do a cryptographic operation against the chip, you have to push your information to the chip and ask the chip to do that validation or whatever else you need it to do. So that's one of the ways that it keeps things like your private key secure. It also has a slot for your device certificate. That is something that is write once, but you can read this. If you're re-rolling your certificates, that can be a little bit of a problem. So there are other slots in here that are aux slots that you can write to multiple times. So if you've got a rolling certificate strategy or something like that, use the aux slots, don't use the primary slot. So I said you have to push stuff. You push your requests into the chip. You ask the chip to do things for you. So how do you ask the beam to do your cryptographic operations against the crypto chip? This is a little bit of source code that does that. This is all in the NervesKey repo. So I'll only go through the important parts here, and you don't have to memorize it. You can take a look in the NervesKey repo there. Long story short, you load up an engine here, and this is that reference to the chip. This is how the beam knows that when you need to do one of these operations, it needs to go out to the chip and not use like a private key file to do that. I said these work over I2C, so we initialize just an I2C bus for this chip to connect with. From there, we're just getting certificates, keys, and so on. And in this case, when we're starting up a Tortoise connection, we just dump that information there in the cert and key and CA fields, and it connects. So how do you actually get some of the hardware? What are some of the different variants that this looks like? You already heard me saying NervesKey is a library. That's also a physical piece of hardware. This is something that's made by Frank, although last I talked to him, no longer made by Frank, and I believe he might be looking for somebody else to pick this up if anyone's interested. Thumbs up. Okay, John's saying correct information, not something to add. So there's that. If anyone's interested in helping with that, that's something that's out there. I do have another hack to this, though, another alternative that's up my sleeve, and that's the SparkFun board that they call the cryptographic coprocessor. It's just an ATECC chip on a board with a quick connector and a pin header. So very similar. The NervesKey has a Raspberry Pi header form factor. This one, if you're not using Quick, well, Quick is pretty plug and play. If you're not using Quick, then you have to do a little wiring down here to get it to the right pins, but it's not too hard. So this is the kind of thing that could be used in development, probably even low level, like prototyping, production type stuff. There's another method that I love to use, and that's an SOIC8 breakout board. So we just have a fistful of crypto chips on hand. Anytime we need to use one for development, we just grab one, solder it to a board. It's not that hard to do, or at least for us, it's not that hard to do. So that's an option there. That's probably one of the lower costs in terms of development type stuff. If all of this is still looking overcomplicated, don't worry, I also have you covered too. You can get this chip built into development kits as well. So the microchip SAM A5D27 is a development kit that has the crypto chip built onto it. It's on their WillSOM1 module here. So the cool thing about this is you can do your development on the dev kit. And if you need to build a little bit of electrical hardware out, but you don't want to worry about designing out the CPU and the memory and all the, I'll say the hard stuff, you can buy the SOM from them here with the crypto chip on it, and you can place that on your board. And now everything still feels pretty familiar to what you were dealing with in development. And we do provide a nerve system for this microchip dev kit in the SOM. If this is still looking too complicated though, a very off-the-shelf solution is the recomputer. You can order the recomputer with a crypto chip built into it. And normally, this is where a Nerves presentation would end. However, there's another way you can do this, and that's with a TPM, or Trusted Platform Module. This is cool because it's an open piece of technology. So the Trusted Computing Group publishes an open spec, the TPM 2.0 spec here. Contrasted to Microchip, Microchip doesn't have a lot of public information available about their chip, so it's a proprietary chip. There is a public data sheet available, but it's very, very limited. Really, if you're doing like serious development against the ATECC crypto chip, you're going to want the full data sheet. That does require an NDA and some other hoops they make you jump through. So this is open. And that also means there are other hardware vendors available to get it from. So Microchip does make TPMs as well. ST Micro makes them, and so does Infineon. This can be really, really nice if you have to worry about supply chain diversity or worry about an alternate supplier. I remember back in the supply chain crunch in 2000, the Microchip crypto chips pretty much dried up. They were really hard, if not impossible to get. And I hate to say it, but I do remember seeing projects go back to using file-based certificates in that case, just to be able to ship. So that didn't feel great. So this is another cool option here, is at least you've got alternate vendors in this ecosystem to be able to go with. The interfaces are really nice as well. It's what you'd expect, I2C or SPI, so pretty easy to integrate into just about any hardware out there. Like the crypto chip, the TPMs also deal with memory. They understand it more in terms of addressing than slots. So you have addresses and handles that you work with. Some of those ones that are interesting that we care about here are the persistent memory, the permanent memory, and there's also non-volatile memory, and we'll get into that in a bit. There's a couple ways you can interface this into the Beam or like into OpenSSL in general. The first one is through an OpenSSL provider. That's the new OpenSSL API as of version 3. Unfortunately, the Beam doesn't support OpenSSL providers yet, though. So we're looking forward to this one. You can't quite do it with the Beam yet. We're using the OpenSSL engine instead, which is the same way, honestly, that the ATECC crypto chip is doing it. So everything should still feel pretty familiar there. You can also do it through PKCS11. That's its own can of worms, though, so I'm not going to talk about it, but just know if you need PKCS11, you can do it. And there is a ton of hardware that's coming out either with TPMs already on it or the option to order a TPM attached to it. So just the ecosystem of development kits or basically off-the-shelf computers that you can ship straight to the field is just amazing. We love this part. And so when you're dealing with testing too, maybe your testing stops at hardware. Maybe that's as much as far as you've run your application. Although in our case, we also like to be able to run our firmware application on our development computers. So on the host computer, Nerves calls it. We also like to be able to run it in CI in the cloud. And so if you've got this physical ATECC crypto chip that's a proprietary spec, how do you do that? And at least our solution to doing that has been dependency injection. So we write one implementation for the hardware to actually be able to connect when the crypto chip is available. And then we've wrote a second implementation that's the injection into host or CI when the crypto chip's not available. And honestly, that one does use files. It doesn't make me feel great, but that's how it worked. So the cool thing here, as I said, the TPM is an open spec. So instead of only implementing against hardware, what if you also have a software variant? So IBM wrote a software TPM. It's the same API, same interface as a hardware TPM. And now you've got something you can run on your host, you can run on your CI server. And now instead of having two different implementations that you have to have for hardware versus no hardware available, versus CI, this is just a configuration change. In one of the config files, we can just say, hey, when we're on the hardware configuration file, change one line to say this is where the TPM is located at. And when we're in the host config file, we change that line and say this is where the software TPM is at. And the application doesn't have to know the difference between the two. The application just says, I need to talk to a TPM. So if this is looking cool, how do you start integrating with this with Elixir? First of all, there's two libraries that we have published up to Hex that do this. The first one, TPM, is for working with the hardware side of things, or well, just TPMs in general. SWTPM is the one that specifically helps you work with the software portion of this, the software TPM from IBM. If you're working with an official Nerve system or you've built a custom Nerve system, you probably don't have the TPM packages built into your system yet. So you'll need to add those to the Nerves def config. That's not really too hard to do. You just need to put these packages in. You will have to recompile your system in that process. But that's what it takes to bake that in. If you're using one of the Redwire Labs Nerve systems, we are starting to bake this into our systems. So you'll get that out of the box. Now that we've got the system part out of the way, we can go up to application land now. And so our application, first of all, can generate a private key. It's as simple as TPM gen key. And then this thing that suspiciously looks like a file, and I might have just told you how evil files are earlier. So the catch to this. This is the provider versus engine thing I was talking about earlier. At the point where the Beam is able to support providers, it looks like we'll probably be able to get rid of the file portion altogether while we're still using the engine method. This file isn't actually the key itself. You can think of this more like a handle or a pointer into the TPM. So it's something that just OpenSSL needs floating around because of the methodology for some reason. If you move this file to another system, you can't gain access to those credentials. This file doesn't work separate from the TPM. So this is more of like a reference to stuff that's on the TPM. And you just kind of have to store it on disk as long as we're doing an OpenSSL engine. So then kind of like the ATECC crypto chip, how do you plug this into the Beam and kind of what comes back in that private key? So when we're getting a reference back to that private key here, normally when you're using files, this is just like the file itself or a reference back to that file. In this case, since we need to use the crypto hardware, the Beam gives us back an engine key reference. And this is a little piece of magic that tells the Beam, hey, go out and use the crypto chip when you need to do this, or the TPM in this case. So there's an engine reference, a key ID. If your key is password protected, that's where the password goes. And then there's some Erlang magic in here. Honestly, we've never had to set those parameters. So now that you've got a private key, this should probably be looking pretty familiar here at this point. Derive a public key from it. All of this works with the X509 Elixir library, so you can use those functions like you're used to. So in this case, we'll convert it to PIM. I mentioned the certificate authority earlier, so we'll take the private key and we'll generate a certificate signing request here. And again, this is the point where we can put that device ID into the certificate. So this would be like the serial number, for example. We can also attach that to an organization. And again, we'll convert that to a PIM because in this case, we'll say we're sending it up to a signing server. There are a couple different ways that you could sign your certificates. So I'll gloss over some of the specific details there. We'll say we've got a signed certificate that comes back and we've stored that as well. Now we're ending up with, again, a bunch of files on disk. And I just mentioned the files on disk don't feel good. So this is where that NVRAM comes into place. This is the non-volatile memory on a TPM. This is basically user space, is how you can think of it. You can do anything you want with this block of memory. So we use NVDefine to ask the TPM for a 1K block of memory. We'll take that private key, well, the reference to the key, and we'll put that in that address. Likewise, we can back up the certificate bundle in there, any of the other important stuff that we might need. So now we go through and configure the SSL connection in the engine to do that. So again, get a reference back to the private key. Here I'll just show how to be able to get that right out of the NVRAM if you want to. So you can use NVRead to go read the certificate address. This is an address that we just made up and got earlier. We backed it up in there as PIM. So we can go from PIM to the Elixir 509 struct, so we can use it natively. The Beam likes to use a lot of things in dir format, so we'll convert this to dir before it actually goes out to the Beam. And then in this case, we'll start up EMQTT. Oops. And again, you just put the key in the cert in the SSL ops, and it'll go off and connect. So a really cool thing about being able to back stuff up in the NVRAM is now you could reformat that disk either as part of a factory reset, or if a user wipes stuff out, or something goes wrong with your system, if you need to RMA it and you still need to know something about that device's credentials, you've got this backed up in the TPM. One of the things that you could do that we like to do is when your application starts up, it could go check the TPM addresses, the NVRAM addresses, to see if anything's in there. It can check the file system, and if it's not on the file system, it can move all those references back to the file system and everything just kind of works again. And so if this is looking like a lot of Elixir magic at this point, also don't worry, it's just Linux. So because this is an open spec, there's a bunch of TPM tooling out there and command line tooling that exists for this. Really what we've done here is wrapped that command line tooling for the processes that are important to go through in Elixir, exposed that in a more idiomatic interface, so it just feels like Elixir at that point, so you're not trying to send command line commands from Elixir itself. But the caveat to that is we also haven't implemented everything too, because it's massive what you can do with those commands. There is a lot to go through. So rather than reinventing the entire wheel, we decided we'll kind of do the happy path through it, the stuff that you're most likely to use. And if there's something that we either missed that you need, or you don't like the way we did something and you want to break out and, at a certain point and do something else the way that you'd rather do it, you can absolutely do that. You can call these commands directly. So that being said, what questions do you have for me? Oh, I thought I left everybody speechless. One sec, John's got the mic for you.
Oh, perfect. Thank you. TPM versus Secure Enclave by Microchip. Are they similar, just the TPM is open, or was there other differences that I missed?
If you're working in Nerves land, they will feel very similar to you, except the TPM will give you a lot more options. If you're like us and you're helping develop behind the scenes on the technology, it's a little more complicated. And that's where you run into some of the microchip pain points. So actually having data sheets available to do that and those kind of things.
So your previous slide, it's just Linux. Maybe this is out of scope, but it is just Linux, and just Linux is Frank does not have 51% of code contributions to Linux. That's a platform that is a little bit beyond nerves, right? And so a lot of this security, web transport stuff, but what about security on the way down into we have a wrapper around the Linux command, the Linux program for this. Are there concerns, ways to mitigate, someone's man in the middle inject something on the way to that program and alter whatever it's doing? Or, where do those concerns end?
Welcome to my next talk. So yes, those are things to be thinking of. That's kind of a completely different topic, and a whole different set of security concerns. But you're probably more dealing with like Linux C groups and things like that at that point. You're beyond the connection at that point, and you have a different set of problems.
Yeah, no, that's fair.
Yeah.
So you talked a little bit about using like a VPN in the beginning, and I think that still comes down to you have to store secrets on a device somewhere. But I was curious if you have opinions on services like Tailscale or Remote It, where you're creating like a virtual VPN.
That's a good question. I do tend to be a person with lots of opinions. Trying to form some around here. I'd say those are great services. Those are good things to be using. It's really probably the question around that is how much or how little DevOps work or infrastructure work do you want to be putting into that? What capability does your team have? Things like that. That's going to be one of those big things that drives. Do you pull an off-the-shelf service, to do that really if I remember right, Tailscale just uses WireGuard under the hood. So, do you offload the cost and put it into a SaaS platform where you're getting charged monthly for it, or would you rather do it up front and pay your engineering team to do it, where it's probably more expensive up front, but it's going to ideally cost you less over the long term? Either technology is great. I think it really just comes down to a business decision of what's right for you. I think John was next, and then Chris.
Have you had to argue with clients or other people more about how security is a lie when you give physical access to a device? Do you have to get in depth to some of these situations where a very, very motivated actor could still reclaim electrical signals in some sort?
So you ask this question and you see the pain on my face, because I'm pretty sure it sounds like this is leading into you've been down this path, and you're looking for somebody to share your pain, and don't worry, I do.
Yeah, maybe adapted. Do you have any advice for those situations when you're reviewing your scale of security that's acceptable versus not acceptable?
I mean, yeah, I think that honestly, I think the bigger problem I've had there is there seems to be like two groups of people, those who listen and those who don't want to. And for those who don't want to, there's kind of, I don't know, I haven't found a good way to get through there yet. I think there's just some people that are just not going to do it and they don't care about it. Hopefully there's now a presentation that you can be linking to those people that says, here, go do this thing. But yeah, really, I don't know. For me, it's just been more a matter of spending the time with the people who do listen and helping them improve their practices, and the people that just don't have the security mindset are just going to do what they want to. So I don't worry about them.
So I guess the root of the question is, are you seeing potentially the microchip fading out in favor of TPM through the community? Is that something, you kind of want to support or drive, or just so that we're more vendor agnostic, or where are you seeing this going as a community?
That's a really good question. I think the first priority and the biggest thing that I see around that really ties into what John just asked is the biggest thing is, for the love of God, get off of files. Like, that's one of the huge things in the community where people are just like, I'll just dump my private key on my Raspberry Pi and everything will be fine. If you're doing it with like a hobby project or it's just your own personal stuff or whatever, that's fine. Like, that's kind of out of the scope of the presentation. I'm talking about like actually shipping a professional product, like somebody just paid you money to do this. There should be a security focus and an element of responsibility around that. So that being said, any hardware option right now is better than no hardware option. And that's my main point. If you're in ATECC crypto chip land, sometimes things might have worked well for you. Like what Ben brought up, for example, like when we used to work on that system, that has the SOM in it. It's really convenient just to use the SOM and have the crypto chip on there and ship the product. That's a great approach. The supply chain crunch is a really good example where it's like, if you're so dependent on the crypto chip, you have zero alternatives. That's one of those problems. Or the crypto chip, if you don't have the ability to develop your own custom hardware, you're locked into a certain, a more limited set of development kits, a more limited set of SOMs. Your world of hardware is smaller. So a TPM is really one of those things that can help expand your world of hardware to be able to get possibly a piece of hardware that fits your use case better. And now here's a solution that helps do that.
Okay. And then just to follow up on using like Tailscale VPN, one thing that's very easy to forget is there is a secret in there to connect to those services. And that's where it seems really simple. I just stuck it in a config file and it magically worked. But do always think about how you're connecting to those services and push those secrets down into a hardware chip. And don't just burn it into the firmware because it's not magically hidden by Mixcompile.
Yep. Anybody else?
I'm just wondering if you have a sort of standard framework when you work with clients to determine how many layers of the onion in security. Do you just sort of have a standard, hey, this is what we do typically do? Or do you work with each client to determine sort of how many layers of security you're going to put in place?
The general answer is yes. So it's a blend of both. And that's probably really just what good consulting comes down to. So some cases, it's really determining for each one of those cases, do you need to lean more towards an off-the-shelf option, or do you have the capabilities where a more custom approach works for you? A lot of that ends up coming down to business reasons and budget and things like that. So there's options on both ends. And that's one of the reasons why I like the TPM, for example, with like opening up more hardware, because now there's this extra layer of like detail that you can dive into for how much you need to customize versus how much you can get off the shelf. It's not so black and white anymore, which is nice because that helps each client kind of slot into their own custom path without having to go full custom hardware. We have done full custom hardware though, so that option's there too.
Hi, just a comment. So I've been working with the European Union for the last 2 years on the Cyber Resiliency Act and a whole bunch of stuff that they're doing. And a comment to your observation is you collectively need to think about what market segments and verticals you're in and whether you're going to have to put TPMs in there. The law is very general in the sense that it says you need to use industry best practices. So, and they have a very clear definition of verticals that require TPMs, and they'll expect those to be there, and the others that don't. That clearly they have separate guidelines and stuff for healthcare monitoring and other bits and pieces that you need to have out there. So if you're generally in this space, you better be able to do everything from not give a hoot and continue to write stuff on file systems to be able to do everything up to post-quantum cryptography TPMs. The Infineon guys just recently got a prize for delivering the first post-quantum crypto algorithms in silicon or whatever it is, right? So you need to be thinking about how long you're going to have your fleet out there, and how successful you are, and what you want to go do, and how you want to age these things out. Because if the worst attitudes or views of post-quantum cryptography and the speed with which these things are going to come along, you're going to have an obsolete fleet if you've not planned. But you could also spend way too much money up front and not get the utility you have. So you need to think about the business model and the place that you're in. So
Absolutely.
We allowed to do that?
You are allowed. Building on the previous gentleman's question, there are a couple of InfoSec researchers that publish frameworks that are really applicable to this kind of development work. I will find a couple of them and I'll get them to Alex to distribute. But allow me to evangelize a little bit in the form of a rant. Even though Alex gave us all permission to just, throw secrets on a file when you're doing development, please do not do that. Start to build up the knowledge base and the muscle memory to put these techniques in practice. You will learn a lot. You will become more marketable. You'll become a better developer, and your stuff will be more awesome. You don't know how long your material will be out in market. You don't know what size footprint you will have. It doesn't necessarily mean you have to have 1 million devices out for somebody to weaponize it. There are instances of people weaponizing light bulbs and, very benign IoT devices that then get them to escalate to other devices and other privileges. Don't allow that to happen with your stuff. And it's kind of fun actually to figure out how to do a little belt and suspenders with combining some of these things to make it the time cost really hard to compromise a device. And you'll learn a lot more, and it becomes part of your repertoire. So I would highly encourage you to, take 20, 30 minutes to learn some of these frameworks and then figure out ways to put them in production for your own designs.
Absolutely. And I should clarify one of my comments based on what you said, because I might have said it wrong. If you're doing this commercially, absolutely don't use files. Where I was trying to say it's okay to use files is if you're doing this for a hobby project to learn how this stuff works. Like if this is just going to be a little home automation thing that sits in your house and it's just on your own little network and nobody else is going to touch it, that's a great way to experiment through this. If you are charging people money to do this stuff, for the love of God, do not put files on their system, file-based keys on their system. Anybody else? Cool.
All right, last one. What do you think about security through obscurity approaches, like using Halo plus some secure chip that requires an NDA? And it could be your client ends up feeling better because the documentation is behind an NDA, or could be actually more secure.
You're getting into Apollino territory here. Yeah, you can answer that one first. Yeah.
Simply put, don't do it. When it comes to security through obscurity, there's always a time factor. If someone has enough time and enough will and power, it can be broken. I've broken a lot of security from top 500 companies on apps on the iOS market, applications that actually embedded client certificates. They were encrypted, they were obscured, like you said, but with a little effort, you can break into it, you can decrypt it, and abuse their APIs.
Redwire Labs has no knowledge of what Apollino may or may not have hacked as part of security. Yeah, so that's basically what Apollino said. When it really comes down to it, there's no such thing. Kind of to the other point, it's like, you know, you can kind of jump through some hoops to make an argument of it falls into the bucket of what skill level attacker are you trying to keep out, but somebody can get that information. Cool. Is that it?
I think that's it. A round of applause for Alex.
Thanks, everyone.